So your lesson on 13.2 is going to introduce you guys to what's called the unit circle. So there's quite a bit of vocabulary. The unit circle is really quite strange. Something you've never seen before. So first, we have angles on the unit circle. Always start from an initial side of what we call 0. This guy right here is always our initial side. So the positive x-axis. The unit circle looks really similar to the coordinate plane. There are a lot of similarities. He is superimposed on the coordinate plane technically. But this is always where we start. And then you open angles in a, this is what's really weird, in a counterclockwise rotation. So when I go counterclockwise up to here, that's a 90-degree angle. Can you visualize that from here to here is 90? And then keep going to 180. And then in our case, they wanted us to measure 210 degrees. So we'd go past 180 down to this guy. He's called, whoops, your terminal side. And then it's not just good enough to draw the terminal side. What you have to do then is indicate the direction in which you traveled. Because this is the positive direction. What do you think would happen if I went clockwise? It'd be negative. Very good. So 210 degrees, we just kind of already did that one. So you start at here, and then if you rotate, here's 90, here's 180. How many more degrees below this axis do I go to get to 210? 30, I heard. Very good. So this guy right here is 210. What you're going to do next, just like we did earlier, draw an arrow indicating the direction in which you traveled. And it would be super awesome if you go ahead and write 210 degrees somewhere above it. I know it says it right there, but it's just good habit. Okay, think about 305. You always start here. And then think about traveling 305 degrees. Well, here's 90, here's 180. Keep going. Here's 270. Keep going. Okay. So like maybe down here somewhere. And again, you have to indicate the direction in which you traveled. And then somewhere over here, write down that this was 305 degrees. So the angle is from this blue guy wrapping around to this red guy. Why is it what? This means origin, 0. Is that what you're asking? Okay. So 580 degrees. This is a little complicated. How much would be one rotation? 360. So 580 is going to make one full rotation. And then if I go 90 more degrees, where am I at? 540. And then I need to go a little bit more to 580. So what you're going to do is we know he lands, he terminates somewhere kind of over here. But if you just draw an indicator arrow from here to here, you have not shown me a 580 degree angle. What you're going to have to do is show me that it went through one full rotation plus a little more. Like that. Fun times. 580 degrees. That's why drawing those little squiggles are so important, because if you meant to do more than one rotation, you have to show me that. So as you can imagine, I could have you guys graph really huge angles.
Wouldn't 580 be on the bottom though?
I don't know.
Because after 360, isn't it 220 more degrees?
Okay.
So then you guys.
Oh my gosh, I'm dumb. Thank you, Jared. Okay, I need some calculator help, because I haven't slept again. 540. Yep. How far away from 360 is it? Someone subtract that. 40. More than what I drew. 220. So, Jared was telling me that after you do one full rotation, you have to go 220 more degrees. Think about what that looks like. 180, 220 would be down here. Thank you. If you do one full rotation, that's 360. We have to get to 580. So 220 more degrees. Apparently I can't subtract. So he's actually down here in what we call quadrant 3. Thank you. And that is how you draw it. Woo! Fun times. Thank you. Okay. Can you guys tell me about quadrants real quick? What's this guy called? This is quadrant 1. We signify him with Roman numerals usually. What's this guy called? 2? 3? And 4. So sometimes I'm going to ask you what quadrant does it terminate in, and you're going to have to give me either 1, 2, 3, or 4. Okay, let's keep going. 135. Let's start with the first question I just have. What quadrant will 135 terminate in? Yeah, over here in 2. So this is 180. That would be too far. 135 would be like right here. And then remember, you have to show me your indication of what direction you traveled. So he's 135 degrees. Uh-oh. I mean, I'm not going to count you off if you're like a millimeter in the wrong direction, but 135 degrees would be 45 degrees above 180. So if you kind of think about this being 90 and this being 180, he's smack dab in the middle. Okay, negative 450. First issue I have is we're supposed to be traveling in a negative direction. So instead of going counterclockwise, now we're going to go clockwise. The other issue I have is the fact that I can't subtract. If I did one full rotation negative, that would bring me to negative 360. How much further do I need to go? 90 more degrees. So I'm going to end up down here. And then I can't just label it like that. I need to indicate how I traveled and in what direction. So remember, we started at 0, you went negative, and you did one full rotation plus another 90. And that was negative 450. That's a 50, not an 80. Fun times, right? Trig is fun. Okay, negative 560. So again, I'm going to go clockwise this time because we're going negative, and I'm going to do at least one rotation. Okay, let's see. I need some calculator help. After I go negative 360, how much further do I need to go? Okay, I could do that in my head, I guess. 200 more degrees. So if I go 200 more degrees, what quadrant will you land in? This one right here. Now again, the indication of how you traveled is so important. You guys went negative one full rotation and then another 200 degrees. And that's how you got to negative 560. That is not a 6. Okay. Some of you guys are having a hard time coming up with how many more degrees you travel. If you know that one rotation was 360, you could just subtract them to figure out how many more degrees. Okay. And remember, this is 90, 180, so we went a little more, 200. Okay. The idea of being coterminal means that I'm going to give you 2 different measurements, but if I drew them, they'd land on the same spot. So if you can imagine, let's go back to, okay, this example right here, 305 degrees. Can someone give me another way to land right here? Okay, you're the right idea with negative. But how far negative would you have traveled? 55, right? Because this is 360. So if you back up 55 degrees, you'd land in the same spot. So that's called a coterminal angle. And I know sometimes you guys can visualize it really easily, but most of us would rather just have some way to type it on our calculator. So the idea is when you're trying to find coterminal angles, you either add or subtract 360. And on most questions, I'm going to ask you for a positive and a negative coterminal angle. Now here's the catch. There's like a gazillion answers you can give me because the unit circle never ends. It rotates forever. So could y'all do me a favor and not give me some obscure angle that's like 500 rotations out into space? Because then I got to sit there and go, okay, is it coterminal? On my own calculator, that's annoying. So just do the first one. So 65 degrees. If I want a positive coterminal angle, should I add 360 to this or subtract 360 to that? Thinking adding would be a good idea. So one full rotation would be what measure? What's 65 plus 360? I heard 425. Okay, so there's my positive coterminal angle. And now I want you to come up with a negative one. So start with 65 again. Should I add or subtract 360? Subtract 360. I need help. Negative 190. 295 makes more sense. Thank you. Are those the only 2 answers? No, I could keep subtracting 360 off of negative 295 as many times as I want, and I would give you an infinite number of coterminal angles. But again, do me a favor, don't do that. That's really annoying. Just find the first one. Otherwise, I'm going to be angry. All right, 80 degrees. So give me a positive one. Go ahead and add 360 to it. Yep, 440. So what this means is if I graphed 440, he would land in the same spot as 80 degrees. Yes, ma'am?
Do we have to show our...
No, 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 no. But these are your notes, right? So you want to show as much as you can, because you might wonder how you did this later. And then give me a -1 by just subtracting 360. That'll get you to a negative value. Negative 280. Good. Yep. Yep. Okay, 110. Give me a positive coterminal by adding 360. 470. And then how about a -1? Thank you. I heard negative 250. Is that what I heard? Okay. Now, I have a question. Let's back up a second. What if I gave you like 740 degrees and I wanted a negative coterminal angle? Now, I know in the last few examples we've just subtracted 360. I just made up this example, by the way, not on your paper. Okay, you're on the right track. So subtract 360, and what does that give you? Someone do that.
380.
Positive 380, right? Okay, now what if I subtract 360 again? 20. And then I have to subtract it again. If I asked you for a negative coterminal angle, in some cases you might have to subtract 360 a bunch of times to even get down to a negative number. I sure am. Did I do that right? I feel like I can't subtract today, so. 340, thank you. Oi, maybe I shouldn't have recorded today. Okay, so anyway. Yep. Now again, none of the examples I asked you for had this happen, but I know there is something on your homework where you have to subtract a few times, a few rotations to even get down to a negative value. Now if I asked you for a positive coterminal angle, give me an answer that would have worked for that example. 380, what else? 20. I would have accepted either one of those answers. You also could have added 360. I would have accepted that answer. So as you can imagine, these are a pain in the tushy to grade. Okay. All right, friends. Here is your unit circle. So a lot of these things make sense. It looks like the coordinate plane. You have an x and a y axis. We know that right here is 0. Okay. And you know how to measure it. Normally we measure it in a counterclockwise fashion if you want a positive angle. So we got 90 degrees, 180 degrees, 270, 360, and it goes forever and ever. We typically try to reduce it down to one rotation because it just boggles the mind to think about multiple rotations. Okay, you know how we measure things in feet and inches, miles? What else could I measure distance in? Kilometers, meters, centimeters. So sometimes you have an issue with labels and conversions. Well, the same is true for trig. Yes, we can measure angles in degrees, but we can also measure angles in what's called a radian. Okay. Degrees, you guys know. Radians are a little foreign to you. So for our purposes, because I'm just introducing you to the idea of the unit circle, just believe me that there is something out there called radians. I'm going to tell you how to convert between the two of them, and that's all I need you to know for this class. When you move on to a trig class or a pre-calc class, they're going to go way more into depth as to why radians are what they are, but we're not there yet. We're still doing baby trig. Huh? Well, not radius, radians, a little different. Okay, so if you notice on this unit circle, I've marked a few common measures, 30, 45, 60, 90. And then after that, I've given their radian equivalent. What do you notice about all the radian measures? Pi. They got pi's in them. The ACT likes radian measure because it's nice and clean, and you don't have to use a calculator. Have you ever noticed on your calculator you have two modes, either radian or degree mode? Sometimes we'll want it in radian, and we'll talk about when we want radian and when we don't. Okay, here's the idea. One full rotation. How many degrees is in one full rotation of a circle? 360. Well, can you tell how many radians? 2 pi. So what they've written down here is that 2 pi radians is the same thing as 360 degrees. Well, that's a little too complicated for my brain. So what I do is I divide both of these by 2, because it's like an equation. And then you get pi radians equals 180 degrees. All right, chemistry buffs. Remember stoichiometry? Yeah. Dimensional now? Oh. Okay. You know, as a math teacher, I love stoichiometry because it's very mathy. We're going to do a miniature version of dimensional analysis here with radians. Pi over 180 is pi radians over 180 degrees. But in chemistry, can't you usually take conversions and flip them upside down depending on what you want to cancel out? Yeah. Same happens here in math. It's a beautiful thing. Okay, here's a little box that tells you exactly what you need to know in order to write radian measure into degrees. So if you have radian and you want to convert it to degrees, all you're going to do is multiply by 180 over pi. So what do you think you do if you go the other direction? Degrees to radians. You're going to multiply by pi over 180. So let's try this out. 18 degrees, I want to convert this to radians. Am I supposed to multiply by 180 over pi or pi over 180? Pi over 180. Now, besides the fact that your chart tells you to do that, can someone tell me a label reason why I want to do pi over 180? Getting rid of degrees, and we're keeping radians. So on your calculator, I do not want you to type the pi. Right now what you have is 18 pi over 180. I need you to reduce the fraction of 18 over 180. And you get 1/10, so yes, I heard pi over 10. That is your angle measurement in radians, pi over 10. I will never accept decimals for radians. They always have to be pretty fractions reduced. And you guys have $100 calculators that reduce them for you, so I don't feel too bad. Okay, 6 degrees. Again, to convert to radians, you're going to multiply by pi over 180. So what you have is 6 over 180 pi. Reduce 6 over 180 for me. It's 1 over 30, and they like to put the pi in the numerator. So it's pi over 30. Okay, how about negative 72? Same stuff. Multiply by pi over 180. And I need some calculator help because I don't want to have to think right now. Negative 2/5. So we're going to say negative 2 pi over 5. If you wrote the pi off to the side, it's not wrong. The thing that would be wrong is if you put pi in the denominator. That's way wrong. Yes? How we get pi over 30? 6 divided by 180 is 1 over 30. And then the pi will just pop up in the numerator. Yep. Yes, it'll always be a fraction. It might not be a beautiful fraction, but it's a fraction. They are already... Huh? No. Nope, never. Okay, negative 820 times pi over 180. You getting what to do here? Negative 820 divided by 180. Math, enter, enter, please. What was it? 41 over 9. That sounds more like it. Okay, if you can't read that, that says negative 41 pi over 9. Okay, so the next row, we're going to go the other direction. I'm going to take a radian measurement, and I'm going to multiply it by a conversion to get it to be degrees. What do you multiply 4 pi by to change it to degrees? 180 over pi. Someone tell me, think like a chemistry student, why is it 180 over pi this time? The pi radians will cancel, and what label do you end up with up top? Degrees, just like in chemistry, but way simpler. So, just do that. Pi's cancel, and 4 and 180 are in the numerator, so just multiply those. And just make sure you put a degree symbol on the end. If you don't have any label, like pi over 10 had no label, I know that you mean radians. It's understood that when you write pi over 10, it's in radians. Okay, let's multiply this guy by 180 over pi. I like this way much better. So 5 times 180, careful, the 2 is in the denominator. You're going to divide it by 2. Is it 450? Could someone confirm that?
Yeah.
My brain's a little slow today. Okay. Degrees. Okay, so negative 9 pi over 2, multiply it by 180 over pi. Pi should go. And then you just type away on your calculator. Negative 810? Yes. And negative 7 pi over 12, multiply that by 180 over pi.
So you multiply negative 9.
Tops are multiplied, denominators you divide. What was this one?
Negative 105.
Negative 105 degrees. Okay. Okie dokie. You guys all love trig right now, don't you? Like, this is great. Algebra 2 has a trig component to it. And on the ACT, there are 4 trig questions. Now, 2 of them will be easy SOHCAHTOA kind of questions, and 2 of them will be this more advanced trig stuff. So I want you guys to get all the questions you can correct. So we're going to introduce you to trig. Plus, this is my chance to sell you guys on taking trig next year. Trig's a fun time. Okay, find an angle with a positive measure and a negative measure that are coterminal with each of these angles. Okay, we've done this. You're supposed to add and subtract 1 rotation at least to find positive and negative coterminals. But when we did these problems before, they were in degrees. What are these problems in? Radians. So you have 2 choices. You could convert it to degrees and then convert it back to radians when you're done. But that sounds like a lot of work. Yeah, you'd have to give me your answer into radians, yeah. So if you would like to do all that work, more power to you. Go ahead. I think we have an easier way, although it will involve fractions. So everyone take a deep breath. 1 rotation is how many radians? 2 pi radians. So instead of adding and subtracting 360, we're going to be adding or subtracting 2 pi's. Okay, you can do this, guys. And even if you can't, you got a calculator. I really don't feel that bad. So 2/5 pi. Let's do a positive coterminal angle. I know if I add 2 pi, that'll be a positive angle. Now, those of you who are trying to use your noggin and not your calculator, you'd have to get common denominators, right? What would be your common denominator here? 5. So if you multiply top and bottom by 5, you'd have 2/5 plus 10/5 gives you 12/5. I don't know. Did I do that right? I'm second guessing myself now. Now, if you didn't want to do that in your head, just do 2/5 plus 2, math, enter, enter. What'd you get? 12/5. Ta-da. Okay, now same way to get a negative coterminal angle, you would try subtracting a rotation. So I am kind of overdoing this in my head now. Can someone do 2/5 minus 2, math, enter, enter for me?
Negative 8/5.
Very good. And as long as one is positive and one is negative, we've done our job, we're done. Now again, you could have changed everything to degrees and then back to radians, but do we all agree that would have been like a lot of work and probably not worth our time? This wasn't that bad, especially since you have a calculator. Okay, 5/6 pi. So 5/6 pi, we're going to add a rotation, and then you're going to subtract a rotation. Okay, what'd you get when you added the rotation?
17/6.
Okay. 17 pi over 6. And what about when you subtract a rotation? Negative 7 pi over 6. All right, very good. Okay, bit of a problem here. This is already a negative angle. So keep that in mind. Is it more than 1 rotation? Can you guys think about 3 pi over 2? 3/2 is like 1.5 pi. What's 1 rotation? 2 pi. So we haven't done 1 rotation yet. I was a little worried that we had rotated too many times, but we're good. So I think you just got to add your 2 pi and subtract your 2 pi again. Oh, is that pi over 2? Okay. And then negative 7 pi over 2? Don't believe anything I say. I'm not mathy today. Negative 7 pi over 2? Yeah. Okay. Okay. Not too bad. And again, I don't need you guys to understand the ins and outs of a unit circle this year. I just need you to understand what it looks like, what you can get out of it, how you can convert, and then next year when you do trig and pre-calc, then you can worry about, I don't know. You got it? Okay. Okay, on the back. Another formula, a couple formulas. Arc length and then area of a sector. So arc length is like if I took, let's say, a bicycle tire and I took scissors and I cut off a portion of the bicycle tire. I don't know why I did it. I just did it. Okay. I'm a vandal. That portion of the tire is called an arc length. It's a portion of my, what's it called on a circle when you go around the outside of it? Circumference. It's a portion of the circumference. So again, I don't need to go into great detail as to why it is what it is, but the arc length formula is going to be written like this. S equals R times theta. Theta. Theta is a Greek letter that trig uses to indicate a central angle. It's like an X, they just use a Greek letter theta. Yes. That's the variable they decided to use for arc length. So I might want to write at the top here that that's arc length. What do you think R stands for? Radius, yes. And in this case, it's the literal radius of the circle. And then theta is the central angle. Now here's the catch. Well, that's an L. Theta must be in radians. So if I tell you the central angle is 45 degrees, can you use 45 degrees in this formula? No, you're going to have to convert it to radians. Okay, so there's a little bit of a catch. Okay, area of a sector. Area of a sector, we've all done this. You're looking at a cake, and then you get to cut the cake. So of course you cut a piece of cake that's like this big. That is the area of a sector. So you make your sector much larger than others, and that's okay. So the formula for area of a sector is A equals 1/2 R squared times theta. Well, I'm pretty sure you guys know what these variables stand for. What do you think A is? Area. 1/2 is 1/2. What do you think R is? Radius. And then theta, again, is the central angle. Now, I should have done this down here. Now I realize. S, we decided, was arc length. If you want to write a note to yourself, arc length is a portion of circumference. I can't spell, apparently. Okay, R, you guys told me, was radius. So we're working with a circle, and R is radius. Theta is our central angle. And what did we say about theta? It has to be in what? Radius. Yes. And then A, of course, stands for area of sector. So area of a sector would be like piece of pie. Okay, we are not going to do all these problems because it's a little bit of overkill. We're just going to do a few, and then we're going to move on in life. So, part A, I want you to find arc length. I tell you the radius is 3 feet, and the central angle is pi over 18. Area of arc length, excuse me, is S equals R theta. So, let's plug and chug, people. What's my radius? 3. And then the angle is pi over 18. Good news. Pi over 18 is already in what measurement? Radians. So, I think, in my opinion, because these are application problems, decimals make more sense. Go ahead and crank this on your calculator. What is 3 times pi divided by 18? Use the pi button above the division symbol, I believe. Above the caret. Above the caret, yep. To the 10th place, please. 0.5 roughly?
Yeah.
And then what label would you give for arc length of this particular problem? Feet. It's a portion of the circumference, so it's just feet. Now, same dimensions. Got a radius of 3, central angle pi over 18. This time I want area of a sector. Remember his formula was 1/2 R squared times theta. So let's plug and chug, people. Radius is 3 squared this time. And then theta is pi over 18. Just type the whole thing in your calculator. And to the 10th place, please. .8. And then what label would you give for this? Remember, it's area of a sector. Feet squared. Nice job. Okay, next problem. Radius is 9. Central angle, 60 degrees. Why is that a bit of a problem? It's not in radians. Now, you can either go ahead and convert 60 right now or let your calculator do the work. I like to let my calculator do the work. So arc length is radius times my central angle. But my central angle, how would I convert that to radians? Times it by pi over 180. If you just type all that in your calculator all in one step, you'll get your answer. 9 times 60 times pi divided by 180. Done. I heard 9.4, maybe? And what's my label? Inches, good. Okay, same issue for area of a sector. Well, okay, what happened? Area of a sector is 1/2. Radius is 9. We got to square it for this formula. And then 60 times, you got to convert it to radians, pi over 180. So again, one step on your calculator, it does the work for you. Can someone tell me what they get? I heard 43. What's the decimal? Okay, and what label? Yes, area this time, so it's inches squared. Labels are super important on these formulas. Okay. Oh, that's probably what was said, and I'm just deaf. 42.4? Yeah. Sorry. 42.4, like I said. Is that enough examples of that? Can we stop? All right. Congratulations, we're done.